Welcome to Sleepy Science Odyssey. Tonight, black holes. The most extreme objects in the universe, where gravity becomes so intense that not even light can escape. From stellar mass black holes formed in supernovae to supermassive giants lurking at the centers of galaxies. From the mathematical predictions that seemed impossible to the observations that proved them real. From the warping of spacetime to the quantum mysteries at event horizons. From the paradoxes that challenge our understanding of physics to the phenomena that reveal their existence across cosmic distances. We'll explore what black holes are, how they form, what happens near them, and why they matter for understanding the universe itself. If you're new here, this channel is for people who need something to think about before they can stop thinking. Real astrophysics, no exaggeration, just quiet facts in the dark. Let's begin. Black holes are regions of spacetime where gravity is so intense that nothing, not even light, can escape from within the event horizon. The concept of black holes challenges intuition, describing objects so dense that they fundamentally alter the structure of space and time itself. Unlike ordinary objects that simply occupy space, black holes warp spacetime to such extreme degrees that the normal rules governing matter, light, and causality break down. Understanding black holes requires abandoning everyday experience and embracing the counterintuitive predictions of Einstein's general relativity, predictions that initially seemed so strange that even Einstein doubted whether they represented physical reality. The defining feature of a black hole is the event horizon, the boundary beyond which escape becomes impossible. This boundary is not a physical surface, but rather a point of no return in spacetime. An object crossing the event horizon experiences nothing particularly dramatic at the moment of crossing if the black hole is large enough. Yet from that moment forward, all possible paths through spacetime lead inexorably inward toward the singularity at the center. The event horizon thus divides the universe into two regions. The exterior, where escape to infinity remains possible, and the interior, where all futures end at the singularity. The size of the event horizon, called the Schwarzschild radius, is directly proportional to the black hole's mass. For a non-rotating black hole, the Schwarzschild radius equals 2 times the gravitational constant times the mass divided by the speed of light squared. For a black hole with the sun's mass, this radius would be approximately 3 kilometers. For a black hole with 1 billion solar masses, typical of supermassive black holes at galaxy centers, the Schwarzschild radius would be approximately 3 billion kilometers, roughly the distance from the Sun to Uranus. Despite enormous mass differences, the basic physics governing these objects remains the same. The concept of an escape velocity provides intuitive understanding of event horizons, though the full picture requires general relativity. Any object on a planet's surface must reach escape velocity to permanently leave that planet's gravitational influence. For Earth, this velocity is approximately 11 kilometers per second. For more massive and compact objects, escape velocity increases. At the event horizon of a black hole, escape velocity equals the speed of light. Since nothing can exceed light speed according to special relativity, nothing inside the event horizon can escape, not matter, not radiation, not information. However, this description using escape velocity is somewhat misleading because it suggests that something traveling at exactly light speed could escape from the event horizon. The reality, according to general relativity, is more absolute. Spacetime itself is so warped at the event horizon that all future-directed paths lead inward. Light emitted outward from just inside the event horizon doesn't fail to escape, but rather has no outward direction to travel. The geometry of spacetime makes inward the only possible direction. This distinction, though subtle, reflects the profound difference between thinking about black holes in Newtonian terms versus understanding them through general relativity. The singularity at a black hole's center represents a point where spacetime curvature becomes infinite and the known laws of physics break down. For a non-rotating black hole, the singularity is a point, a zero-dimensional location where all the black hole's mass is concentrated. For a rotating black hole, the singularity becomes a ring, a one-dimensional circle. At the singularity, densities, temperatures, and tidal forces all approach infinity, creating conditions where quantum effects should become important, but where our current theories, general relativity for gravity and quantum mechanics for other forces, cannot be reconciled. The singularity thus represents not just an extreme physical condition, but a boundary of our understanding, a place where our best theories predict their own failure. The question of what exists at the singularity remains unanswered and possibly unanswerable. Many physicists suspect that singularities represent artifacts of classical general relativity, and that a proper quantum theory of gravity would resolve them into something less pathological, perhaps regions of extremely high but finite curvature governed by quantum gravitational effects. String theory, loop quantum gravity, and other approaches to quantum gravity predict various modifications to singularities, but without empirical tests, impossible given that singularities are hidden behind event horizons. These remain speculative. The cosmic censorship conjecture, proposed by Roger Penrose, suggests that singularities are always hidden behind event horizons, preventing them from affecting the external universe, but this conjecture remains unproven. Black holes are characterized by remarkably few properties given their complexity. The Noether theorem states that black holes are completely described by just three quantities: mass, angular momentum, and electric charge. All other information about the matter that formed the black hole, its composition, structure, history, is lost, presumably radiated away during collapse or swallowed by the singularity. This simplicity seems to violate the principle that information is conserved in quantum mechanics, creating the black hole information paradox that has occupied theoretical physicists for decades. The mass of a black hole determines the size of its event horizon and the strength of its gravitational field at any given distance. Black holes range from a few solar masses for stellar mass black holes formed in supernovae, through intermediate mass black holes of hundreds to thousands of solar masses, whose formation mechanisms remain debated, to supermassive black holes of millions to billions of solar masses found at galaxy centers. The mass determines observable effects including gravitational lensing strength, orbital velocities of nearby matter, and the frequency of gravitational waves emitted during black hole mergers. Angular momentum describes the black hole's rotation. A non-rotating black hole has zero angular momentum and is described by the Schwarzschild solution to Einstein's equations. A rotating black hole has non-zero angular momentum and is described by the Kerr solution, which is more complex and includes additional features including an ergosphere, a region outside the event horizon where spacetime is dragged along with the black hole's rotation so strongly that nothing can remain stationary. The maximum possible angular momentum for a given mass corresponds to a maximally rotating or extremal Kerr black hole where the event horizon approaches the singularity. Real astrophysical black holes likely rotate at substantial but submaximal rates, having acquired angular momentum from the matter that formed them. Electric charge is the third parameter describing black holes, though astrophysical black holes are expected to have negligible net charge. Any significant charge would be quickly neutralized by attracting opposite charges from surrounding plasma. Charged black holes are described by the Reissner-Nordström solution for non-rotating charged black holes, or the Kerr-Newman solution for rotating charged black holes. These solutions have interesting theoretical properties, including the possibility of naked singularities, singularities not hidden behind event horizons, if charge or angular momentum exceeds certain limits, though such configurations may be unstable or forbidden by cosmic censorship. The concept of black holes emerged from mathematical solutions to Einstein's equations of general relativity. The theoretical prediction of black holes predates observational evidence by more than half a century, emerging from the mathematical structure of general relativity almost immediately after Einstein published the theory in 1915. This history illustrates how mathematical reasoning can reveal phenomena so extreme that even their theoretical discoverers doubt their physical existence. Yet nature ultimately vindicates the mathematics. Karl Schwarzschild found the first exact solution to Einstein's field equations in 1916 while serving in the German army during World War I. Remarkably, Schwarzschild derived this solution just months after Einstein published general relativity, calculating the spacetime geometry around a non-rotating, spherically symmetric mass. The Schwarzschild solution describes spacetime outside any spherically symmetric object, from planets to stars to what we now call black holes, with accuracy that makes it essential for GPS satellites and other practical applications. The Schwarzschild solution contains a coordinate singularity at a radius equal to twice the gravitational constant times the mass divided by the speed of light squared, the Schwarzschild radius. At this radius, certain coordinate components of the metric become infinite, initially leading physicists to believe this represented a physical singularity where the theory broke down. For decades, the physical interpretation of this radius remained unclear, with many physicists, including Einstein, believing it represented a mathematical artifact without physical meaning, particularly since the Schwarzschild radius lies inside all normal stars, where Schwarzschild's external solution doesn't apply. The understanding that the Schwarzschild radius represents an event horizon rather than a physical singularity emerged gradually through work by multiple physicists. Arthur Eddington and David Finkelstein showed in the 1920s and 1950s, respectively, that the singularity at the Schwarzschild radius is merely a coordinate singularity, an artifact of the particular coordinate system used, rather than a physical singularity. By choosing different coordinates, spacetime can be described smoothly across the Schwarzschild radius, revealing it as a boundary of a different sort, the point of no return where escape becomes impossible. The realization that matter could actually collapse to form event horizons came through work by Subrahmanyan Chandrasekhar, J. Robert Oppenheimer, and others in the 1930s. Chandrasekhar calculated that white dwarfs, stellar remnants supported by electron degeneracy pressure, have a maximum mass of approximately 1.4 solar masses, now called the Chandrasekhar limit. Stars more massive than this limit cannot be supported by electron degeneracy and must either shed mass or continue collapsing. Oppenheimer and his students later showed that neutron stars, remnants supported by neutron degeneracy pressure, also have maximum masses of approximately 2 to 3 solar masses, and that more massive remnants would continue collapsing indefinitely. Oppenheimer and Hartland Snyder published the first description of gravitational collapse to a black hole in 1939, showing that from an external observer's perspective, a collapsing star approaches, but never quite reaches the Schwarzschild radius, with light from the surface becoming increasingly redshifted and dimmed until the star effectively vanishes. From the perspective of matter on the collapsing star, the collapse proceeds rapidly through the Schwarzschild radius and continues inward to the singularity in finite proper time, the time measured by clocks on the collapsing matter. This dramatic difference in perspectives, external observers seeing eternal approach, while internal observers experience rapid collapse and destruction, reflects the extreme spacetime warping near black holes. The term black hole was coined by John Archibald Wheeler in 1967, though he was popularizing a phrase already in informal use. Previously, these objects had been called frozen stars or collapsed stars, terms that emphasize the external perspective where collapse appears frozen near the event horizon. Wheeler's term captured the essential feature that these objects are black, emitting no light, and that they are holes in spacetime, regions from which nothing returns. The vivid terminology helped shift thinking about these objects from mathematical curiosities to potentially real astrophysical phenomena worth searching for. Roy Kerr's discovery of the solution describing rotating black holes in 1963 was a major breakthrough, as real astrophysical black holes inevitably rotate, having formed from rotating matter. The Kerr solution is considerably more complex than the Schwarzschild solution, with the spacetime exhibiting frame dragging, rotation of the black hole literally dragging spacetime along with it. The Kerr metric includes an ergosphere outside the event horizon where observers are forced to co-rotate with the black hole, and predicts that rotational energy can be extracted from black holes through the Penrose process, where particles entering the ergosphere can split, with one falling in while the other escapes with more energy than the original particle had. Stephen Hawking and Roger Penrose proved important theorems about black holes in the 1960s and 70s, establishing that singularities are generic features of gravitational collapse rather than artifacts of special symmetries in the solutions. The singularity theorems show that under reasonable physical conditions, positive energy density, and the validity of general relativity, singularities are inevitable once collapse proceeds beyond certain points. These theorems don't describe what singularities are like, but prove that spacetime geodesics, the paths followed by freely falling particles, must end, indicating fundamental limits on predictability even if quantum gravity resolves classical singularities. The laws of black hole mechanics, formulated by Hawking, Bardeen, and Carter in the early 1970s, revealed deep analogies between black holes and thermodynamics. The first law relates changes in black hole mass to changes in area, angular momentum, and charge, analogous to the first law of thermodynamics relating energy changes to work and heat. The second law states that the total area of event horizons never decreases in any physical process, analogous to entropy never decreasing. The third law states that extremal black holes cannot be reached through physical processes, analogous to absolute zero being unreachable. These analogies initially seemed merely mathematical curiosities, until Hawking's discovery of black hole radiation made them physical identities. Hawking radiation reveals that black holes are not perfectly black, but emit thermal radiation through quantum processes. Stephen Hawking's 1974 discovery that black holes emit thermal radiation represents one of the most important results in theoretical physics, connecting general relativity, quantum mechanics, and thermodynamics in unexpected ways. This discovery transformed understanding of black holes from purely classical objects to quantum systems with thermodynamic properties, while creating profound puzzles about information conservation that remain incompletely resolved. The mechanism of Hawking radiation involves quantum field theory in curved spacetime. Quantum field theory describes vacuum not as empty space, but as seething with virtual particle-antiparticle pairs that constantly appear and annihilate over extremely short timescales, too brief to violate energy conservation according to the uncertainty principle. Normally, these fluctuations have no observable consequences, but near event horizons, the extreme spacetime curvature creates conditions where virtual pairs can become real. When virtual pairs form near event horizons, the intense tidal forces can separate them before they annihilate. If one particle falls into the black hole while its partner escapes to infinity, the escaping particle becomes real Hawking radiation. From a conservation perspective, the infalling particle has negative energy relative to external observers, possible only inside ergospheres and near-event horizons, so the black hole loses mass equal to the escaping particle's positive energy. Over time, this process causes black holes to evaporate, with small black holes evaporating faster than large ones. The temperature of Hawking radiation is inversely proportional to the black hole's mass, given by Planck's constant times the speed of light cubed, divided by 8 times pi times the gravitational constant times the black hole mass times Boltzmann's constant. For solar mass black holes, this temperature is approximately 60 billionths of a Kelvin, far colder than the cosmic microwave background at approximately 2.7 Kelvin. So stellar mass black holes currently absorb more radiation than they emit and are growing. For smaller black holes, temperatures increase dramatically, with black holes of approximately 10 to the 11th kilograms having temperatures around room temperature, and smaller black holes being hotter. The luminosity of Hawking radiation, the rate of energy emission, is inversely proportional to the square of the black hole's mass. This means smaller black holes radiate more intensely, creating a runaway process. As black holes evaporate, they become smaller, hotter, and more luminous, accelerating evaporation in a feedback loop. The final stages of evaporation proceed extremely rapidly, with the last second of evaporation releasing approximately 10 to the 30 ergs, comparable to a large nuclear bomb. However, stellar mass black holes require approximately 10 to the 67 years to evaporate completely, far longer than the current age of the universe of approximately 14 billion years. So Hawking radiation has negligible practical effect on astrophysical black holes. Primordial black holes, hypothetical black holes that might have formed in the early universe from density fluctuations, could be much smaller than stellar mass black holes and could be evaporating today. A primordial black hole that formed with mass around 10 to the 15th grams would be completing evaporation now, having been sustained for the universe's lifetime at the brink of dissolution. Such evaporating black holes would produce characteristic gamma ray signatures, and searches have been conducted, but no confirmed detections exist. The absence of detection constrains, but doesn't rule out primordial black holes as dark matter candidates. The thermodynamic properties of black holes revealed by Hawking radiation are precisely consistent with the earlier laws of black hole mechanics. The temperature is proportional to surface gravity at the event horizon, while the entropy is proportional to the horizon area. The entropy formula, S equals K times A divided by 4 times the Planck length squared, where K is Boltzmann's constant and A is horizon area, implies that black holes have enormous entropies, far exceeding the entropy of the matter that formed them. For stellar mass black holes, entropies reach approximately 10 to the 60 in natural units, making black holes the highest entropy objects known. The black hole information paradox arises from combining Hawking radiation with quantum mechanics. Information is conserved in quantum mechanics. The state of a system determines its future evolution uniquely, and in principle, past states can be reconstructed from present states. However, Hawking radiation is thermal, characterized only by temperature with no other information content, suggesting that information about what fell into the black hole is lost forever when the black hole evaporates completely. This apparent violation of quantum mechanics unitarity has generated decades of debate and research. Several proposed resolutions exist, none completely satisfactory. One possibility is that information is encoded in subtle correlations in Hawking radiation, invisible in local measurements, but present globally. Information would be preserved, but scrambled almost beyond recognition. Another possibility is that information is released suddenly in the final stages of evaporation, or survives as remnants, stable or metastable objects left after evaporation with infinite information capacity. A third possibility is that information is lost and quantum mechanics must be modified, though this radical option is disfavored by most physicists. Recent work on firewalls, complementarity, and quantum error correction has provided new perspectives but hasn't achieved consensus resolution. The firewall paradox, articulated by Olmeri, Marolf, Polchinski, and Sully in 2012, sharpens the information paradox. If information is encoded in Hawking radiation correlations, as many physicists believe, then particles crossing the event horizon must experience a firewall, a surface of intense radiation, rather than smoothly passing through as general relativity predicts. This contradicts the equivalence principle, the foundation of general relativity, which requires that freely falling observers experience no forces at event horizons of large black holes. The firewall paradox thus creates an apparent trilemma. Either quantum mechanics is wrong, general relativity is wrong, or something dramatic happens at event horizons contrary to classical expectations. ER equals EPR is a speculative proposal connecting black hole interiors to quantum entanglement, suggesting that entangled particles are connected by wormholes, Einstein-Rosen bridges. If correct, this would imply that black hole information is preserved through quantum connections between the interior and the exterior, or between different regions of space, potentially resolving information paradoxes. However, this proposal remains highly speculative and controversial, illustrating how black hole physics continues pushing fundamental theory into uncharted territory. Stellar mass, black holes form when massive stars collapse at the end of their lives. Black holes of a few to tens of solar masses form through gravitational collapse of massive stars in supernovae. representing the endpoints of stellar evolution for the most massive stars. Understanding this formation process requires understanding stellar structure, nuclear burning, and the physics of gravitational collapse, topics that connect stellar astrophysics, nuclear physics, and general relativity. Stars spend most of their lives fusing hydrogen into helium in their cores, with the energy released by fusion creating radiation pressure that supports stars against gravitational collapse. This main sequence phase lasts billions of years for Sun-like stars, but only millions of years for massive stars, which burn fuel prodigiously to support themselves against stronger gravity. When core hydrogen is exhausted, main sequence burning ceases, and stars must adjust to maintain balance between gravity and pressure. For stars more massive than approximately 8 solar masses, the post-main sequence evolution proceeds through multiple burning stages. After hydrogen exhaustion, cores contract and heat until helium fusion ignites, producing carbon and oxygen. After helium exhaustion, similar contractions and ignitions produce successive burning stages. Carbon burning produces neon and magnesium. Neon burning produces oxygen and magnesium. Oxygen burning produces silicon and sulfur. And finally, silicon burning produces iron group elements. Each stage is shorter than the previous one, with massive stars spending millions of years burning hydrogen, thousands of years burning helium, and only days burning silicon. Iron group elements have the highest binding energy per nucleon, meaning fusion of iron consumes energy rather than releasing it. Once a core of iron group elements accumulates, no further fusion can provide pressure support, and the core becomes vulnerable to catastrophic collapse. The mass of the iron core at this critical moment determines the fate of the star. Cores below approximately 2 to 3 solar masses can be stabilized as neutron stars, while more massive cores continue collapsing to black holes. The trigger for core collapse is the combination of increasing mass pushing cores toward instability and photodisintegration of iron back into helium and free neutrons, which absorbs enormous energy and removes pressure support. Additionally, electron capture, the absorption of electrons by protons to form neutrons, removes electrons that were providing degeneracy pressure and releases neutrinos that carry away energy. These processes occur over timescales of seconds once they begin, causing precipitous collapse. During collapse, the core reaches nuclear densities where neutrons are in contact, creating enormous degeneracy pressure and nuclear repulsion that halts the collapse for cores below the maximum neutron star mass. The halting of collapse causes matter still falling inward to rebound off the core, launching a shock wave outward through the star. This shock wave is the supernova, the explosive destruction of the star's outer layers, which releases approximately 10 to the 53 ergs of energy, with most energy carried by neutrinos, but enough energy in the explosion to briefly outshine entire galaxies. For the most massive stellar cores exceeding the maximum neutron star mass, neutron degeneracy pressure and nuclear forces cannot halt collapse, and the core continues collapsing through the Schwarzschild radius to form a black hole. The mass threshold for black hole formation remains uncertain, with estimates ranging from approximately 2 to 3 solar masses, depending on the equation of state of ultradense matter and rotation rates. Direct measurements of neutron star and black hole masses show a gap between the most massive neutron stars around 2 solar masses and the least massive black holes around 5 solar masses, though whether this gap is real or observational bias remains debated. The collapse to a black hole proceeds from the perspective of infalling matter in seconds, with tidal forces becoming infinite at the singularity. However, from the perspective of external observers, the collapsing core appears to slow as it approaches the event horizon, with emitted light becoming increasingly redshifted and dimmed until the core effectively vanishes. The newly formed black hole is initially highly distorted and dynamically evolving, but quickly settles into a stationary Kerr black hole through emission of gravitational waves, a process called ringdown occurring over milliseconds to seconds depending on mass. The neutrino signal from core collapse provides crucial information about the collapse and potentially about whether a neutron star or black hole forms. The duration of the neutrino signal indicates whether matter is settling into hydrostatic equilibrium in a neutron star or continuing to collapse into a black hole. The detection of neutrinos from supernova 1987A in the Large Magellanic Cloud, the only supernova for which neutrinos have been detected, confirmed basic models of core collapse and provided constraints on neutrino properties, demonstrating the power of neutrino astronomy for studying compact objects. Not all massive stars produce observable supernovae when forming black holes. Failed supernovae occur when collapse proceeds so rapidly or the shock wave is so weak that the explosion fails, with the entire star collapsing into the black hole without ejecting the outer layers. Such events would appear as stars that simply disappear, potentially preceded by faint transient emission. Several candidate failed supernovae have been identified through surveys monitoring large numbers of stars, though confirming the interpretation requires excluding other explanations for disappearances, including dust obscuration or intrinsic dimming. Binary systems containing massive stars can have complex evolution affecting black hole formation. If stars are close enough, mass transfer occurs, with material flowing from one star to the other through the inner Lagrange point. This transfer can strip envelope layers from donor stars, affecting their evolution and potentially preventing supernovae. It can also spin up accretor stars, affecting their rotation at collapse and consequently the spins of resulting black holes. Binary interactions can even lead to both stars forming compact objects, creating binary systems containing two neutron stars, two black holes, or one of each, which eventually merge through gravitational wave emission. Supermassive black holes containing millions to billions of solar masses exist at the centers of most galaxies. The discovery that supermassive black holes lurk at the centers of most large galaxies represents one of the great revelations of modern astronomy, transforming understanding of galaxy formation, evolution, and structure. These objects, with masses from millions to billions of times the Sun's mass, fundamentally influence their host galaxies' properties through processes including quasar activity, jets that extend hundreds of thousands of light years, and feedback that regulates star formation. The evidence for supermassive black holes comes from multiple independent lines of observation. The most direct evidence involves tracking motions of stars or gas clouds near galaxy centers, measuring their orbital velocities to infer the central mass. At the center of the Milky Way, infrared observations track individual stars orbiting the central object Sagittarius, an asterisk, with some stars completing orbits in approximately 16 years. These orbital velocities, reaching approximately 5,000 kilometers per second at closest approach, require a central mass of approximately 4 million solar masses confined to a region smaller than Mercury's orbit, a density possible only for a black hole. Similar observations in other galaxies find comparable or larger central masses. The galaxy M87 has a central black hole of approximately 6.5 billion solar masses. M31 has approximately 150 million solar masses, and NGC 4258 contains one of the most massive known black holes at approximately 21 billion solar masses. The correlation between black hole mass and galaxy properties, including the velocity dispersion of stars in galactic bulges, suggests tight coupling between black hole and galaxy evolution, with black holes growing in tandem with their hosts through processes that remain incompletely understood. The origin of supermassive black holes remains one of astrophysics' major unsolved problems. The challenge is understanding how such massive objects form and grow within the age of the universe, particularly given that quasars, luminous active galactic nuclei powered by supermassive black holes, exist less than 1 billion years after the Big Bang. Growing black holes to billions of solar masses in less than 1 billion years requires extremely rapid mass accretion or formation from massive initial seeds, and neither mechanism is fully understood. Several formation scenarios have been proposed. Direct collapse involves gas clouds collapsing directly to black holes with masses of 10,000 to 100,000 solar masses, skipping the stellar formation stage. This requires special conditions, including suppression of molecular hydrogen formation that would fragment clouds, possibly occurring in the first galaxies. Alternatively, supermassive black holes might grow from stellar mass seeds through sustained super-Eddington accretion at rates exceeding the Eddington limit, where radiation pressure would normally halt inflow. A third possibility involves runaway stellar mergers in dense stellar clusters, forming very massive stars that collapse to intermediate mass black holes, which subsequently merge and accrete to supermassive scales. The growth of supermassive black holes proceeds primarily through accretion, the capture of gas and stars from surroundings, supplemented by mergers with other black holes when galaxies collide. Accretion is self-regulating through the Eddington limit, where radiation pressure from material falling onto black holes creates outward force that eventually balances gravitational infall. The Eddington luminosity for a given mass is approximately 1.3 times 10 to the 38 times the mass in solar masses ergs per second. For a 10 billion solar mass black hole, this corresponds to approximately 10 to the 47 ergs per second, the luminosity of approximately 3 trillion suns, illustrating the enormous energy release possible from black hole accretion. Accretion disks form when material with angular momentum falls toward black holes. Rather than falling directly inward, the material orbits while gradually spiraling inward as angular momentum is transported outward through viscous processes or magnetic fields. The disk material heats through compression and viscous friction as it spirals inward, radiating energy across the electromagnetic spectrum. The innermost stable circular orbit around a non-rotating black hole is at 3 Schwarzschild radii, where orbital velocities approach half the speed of light and tidal forces become extreme. For rotating black holes, the innermost stable orbit can be closer or farther depending on whether orbits are prograde or retrograde relative to black hole spin. Active galactic nuclei, or AGN, are galaxies with exceptionally luminous centers powered by accretion onto supermassive black holes. AGN include quasars, the most luminous variety, outshining entire galaxies, Seyfert galaxies, lower luminosity AGN with visible host galaxies, and radio galaxies, AGN with prominent radio emission from jets. The diversity of AGN types partially reflects viewing angle, with unified models suggesting that single underlying structures, supermassive black holes plus accretion disks and obscuring tori, appear differently from different perspectives. Quasars represent views directly into accretion disks, while radio galaxies represent edge-on views where disks are obscured. Jets from active galactic nuclei are among the universe's most energetic phenomena, consisting of collimated streams of plasma ejected at relativistic velocities perpendicular to accretion disks. These jets extend from galaxy centers to intergalactic space, sometimes spanning millions of light years and depositing enormous energy into surrounding media. The mechanism launching jets involves magnetic fields threading accretion disks or spinning black holes, with magnetic field lines twisted by rotation and differential motion until magnetic pressure launches material outward along field lines. The Blandford-Zenagic mechanism extracts rotational energy from spinning black holes, converting it to electromagnetic energy that powers jets. The most spectacular jets produce radio lobes, vast regions of radio-emitting plasma far from the central black hole. These lobes form when jets terminate in intergalactic medium, shocking and heating the medium while creating tangled magnetic fields that accelerate particles to high energies. Synchrotron radiation from relativistic electrons spiraling in these magnetic fields produces the observed radio emission, which can be detected across cosmological distances. Some radio galaxies like Cygnus A have lobes spanning approximately 500,000 light-years, more than 5 times the Milky Way's diameter. Feedback from supermassive black holes profoundly affects galaxy evolution. Jets and winds from accreting black holes deposit energy and momentum into surrounding gas, heating it and sometimes expelling it from galaxies entirely. This feedback can suppress star formation by preventing gas from cooling and forming stars, potentially explaining observed correlations between black hole mass and galaxy properties. Essentially, black holes can regulate their own growth by preventing gas accretion once they reach certain masses, creating self-regulation that produces the observed black hole galaxy relations. The relationship between supermassive black hole mass and host galaxy properties suggests coevolution, though the causal mechanisms remain debated. The most well-established correlation is the M-sigma relation, connecting black hole mass to the velocity dispersion of stars in galactic bulges. This relation holds across 4 orders of magnitude in black hole mass, suggesting fundamental coupling between black holes and galaxies, despite black holes containing only approximately 0.1% of bulge mass. Proposed explanations include feedback processes that affect both black hole growth and star formation. Common gas supplies fueling both processes, or mergers that build both black holes and bulges simultaneously. Gravitational waves from merging black holes provide direct evidence of their existence and properties. The detection of gravitational waves from black hole mergers beginning in 2015 revolutionized black hole astronomy, providing direct confirmation of black holes' existence, measuring their properties with unprecedented precision, and opening entirely new observational windows on the universe. These detections represent culminations of decades-long efforts to build sufficiently sensitive detectors and centuries of theoretical development predicting gravitational waves' existence. Gravitational waves are ripples in spacetime itself, produced by accelerating masses and propagating at light speed. Einstein predicted gravitational waves in 1916 as a consequence of general relativity, though he doubted they could ever be detected given their extreme weakness. The waves are transverse, with spacetime alternately stretched and compressed perpendicular to propagation direction. They carry energy away from sources, causing orbital decay in systems like binary pulsars, where gravitational wave emission has been confirmed indirectly through precise timing measurements showing orbital decay matching predictions. The strength of gravitational waves is characterized by strain, the fractional change in length caused by a wave's passage. For even the strongest astrophysical sources, strains at Earth are approximately 10 to the negative 21, meaning that the distance between objects separated by 1 kilometer changes by only approximately 10 to the negative 18 meters, far less than an atomic nucleus's size. Detecting such minute effects requires extraordinarily sensitive instruments and careful control of noise sources that could mimic gravitational wave signals. LIGO, the Laser Interferometer Gravitational Wave Observatory, consists of 2 facilities in Louisiana and Washington, each with 4-kilometer-long perpendicular arms forming an L-shaped interferometer. Laser light is split and sent down both arms, reflecting off mirrors at the ends before recombining. Gravitational waves passing through the detector stretch one arm while compressing the other, creating path length differences that produce interference fringes in recombined light. The detectors achieved the extraordinary sensitivity required for gravitational wave detection through decades of technological development, including ultra-stable lasers, vibration isolation, vacuum systems, and sophisticated noise analysis. The first gravitational wave detection on September 14, 2015, event GW150914, came from the merger of 2 black holes with masses approximately 36 and 29 solar masses, located approximately 1.3 billion light-years from Earth. The signal lasted approximately 0.2 of a second, sweeping upward in frequency from approximately 35 to 250 Hz as the black holes spiraled together, merged, and settled into a single black hole. The peak gravitational wave luminosity, the rate of energy emission, briefly exceeded the combined electromagnetic luminosity of all stars in the observable universe, though gravitational waves interact so weakly that this enormous energy flux passed through Earth barely noticed. The gravitational wave signal provided rich information about the merger. The early inspiral phase, where black holes orbit while gradually spiraling closer, encodes the individual masses and spins. The merger phase, lasting only milliseconds, captures the moment when horizons touch and merge into a single distorted horizon. The ring-down phase shows the merged black hole settling into a stable Kerr black hole through emission of gravitational waves with characteristic frequencies and decay times determined by the final mass and spin. These 3 phases allow independent measurements of the same system, providing consistency checks confirming general relativity's predictions. Subsequent detections have found dozens of black hole mergers plus several neutron star mergers, revealing black hole populations with diverse properties. Masses range from approximately 5 to over 100 solar masses, with some systems containing unexpectedly massive black holes challenging formation theories. Spins vary from nearly 0 to high values approaching maximum rotation, with spin directions sometimes misaligned with orbital angular momentum, suggesting complex formation histories possibly involving dynamical capture in dense stellar environments rather than binary evolution from stellar pairs. The observation of binary black hole mergers confirmed predictions from general relativity that have no counterpart in Newtonian gravity. The merger produces a final black hole with mass slightly less than the sum of initial masses, with the missing mass, up to several solar masses, radiated as gravitational waves. The relationship between initial masses, final mass, and radiated energy matches numerical relativity simulations that solve Einstein's equations on supercomputers, confirming general relativity in the strong field dynamical regime where gravitational fields are extreme and rapidly changing. Gravitational wave detections enabled tests of general relativity in unprecedented regimes. The consistency of the three merger phases with general relativity's predictions tested the theory where gravitational fields are strongest and dynamics are fastest, conditions impossible to create in terrestrial laboratories and rare in the universe. The wave propagation speed was confirmed to equal light speed to extraordinary precision, ruling out modified gravity theories that predict different propagation speeds. The absence of certain features in signals ruled out hypothetical exotic alternatives to black holes like boson stars or gravastars. The detection of gravitational waves from a neutron-star merger in August 2017, GW 170817, accompanied by electromagnetic observations across the spectrum, demonstrated multi-messenger astronomy's power. This event, approximately 130 million light-years away, produced gravitational waves detected by LIGO and Virgo, followed within 2 seconds by a gamma-ray burst detected by space telescopes, and subsequently by optical, infrared, radio, and X-ray emission observable for weeks. The joint observations confirmed that neutron-star mergers produce short gamma-ray bursts, synthesize heavy elements including gold and platinum through rapid neutron capture, and provide independent measurements of the universe's expansion rate. Future gravitational wave detectors will extend capabilities dramatically. LIGO and Virgo are undergoing upgrades to improve sensitivity, while additional ground-based detectors, including KAGRA in Japan and LIGO India, are joining the network, improving sky localization through additional baselines. The Einstein Telescope and Cosmic Explorer, planned next-generation ground-based detectors, will have sensitivities 10 times better than current instruments, detecting mergers throughout cosmic history. LISA, the Laser Interferometer Space Antenna, planned for launch in the 2030s, will have arms millions of kilometers long in space, detecting lower-frequency gravitational waves from supermassive black hole mergers and other sources invisible to ground-based detectors. Black holes warp spacetime in ways that can be observed through their effects on light and matter. The extreme spacetime curvature near black holes produces observable phenomena that reveal black holes' presence and properties without requiring direct observation of event horizons themselves. These phenomena include gravitational lensing, where light paths curve around massive objects, orbital motion of stars and gas, and characteristic radiation from hot accretion flows. Understanding these observable effects enables indirect black hole detection and study. Gravitational lensing occurs because mass warps spacetime, causing light to follow curved paths around massive objects. This effect, predicted by general relativity and confirmed during the 1919 solar eclipse, becomes extreme near black holes where curvature is immense. Black holes create gravitational lenses that bend light from background sources, producing distorted, magnified, and sometimes multiple images. For perfectly aligned sources and lenses, light is bent into Einstein rings, circular or nearly circular images surrounding lenses, while more typical misalignments produce arcs or multiple separated images. Microlensing occurs when compact objects, including black holes, pass in front of distant stars, temporarily magnifying them. The duration and shape of brightness variations reveal lensing masses, with black hole masses producing timescales of weeks to months for typical stellar distances and motions. Microlensing surveys monitoring millions of stars have detected thousands of events, mostly from stars or stellar remnants, with a few candidates possibly representing isolated black holes. However, distinguishing black hole microlensing from stellar microlensing requires additional observations, including parallax measurements or astrometric microlensing, where source positions shift during lensing events. Supermassive black holes at galaxy centers gravitationally lens background quasars and galaxies, producing dramatic multiply-imaged systems observable across the universe. The most extreme examples create Einstein crosses with 4 images arranged around lensing galaxies, or even more complex configurations with additional images or rings. These lensing systems provide multiple benefits, measuring lens masses including dark matter distributions, probing intergalactic medium through absorption lines at different positions, and measuring cosmic expansion rates through time delays between images that depend on cosmological geometry. The photon sphere defines the radius at approximately 1.5 Schwarzschild radii, where photons can orbit black holes in unstable circular orbits. Photons at this radius experiencing even slight inward perturbations spiral into black holes, while slight outward perturbations allow escape. The photon sphere creates the black hole shadow, a dark region in images larger than the event horizon where light emitted or reflected near the black hole is captured. For a non-rotating black hole, the shadow radius is approximately 2.6 Schwarzschild radii, while rotation and viewing angle modify this prediction. The Event Horizon Telescope collaboration produced the first image of a black hole's shadow in April 2019, observing the supermassive black hole at the center of M87. This observation required coordinating radio telescopes worldwide to form an Earth-sized virtual telescope through very long baseline interferometry, achieving angular resolution of approximately 20 microarcseconds, sufficient to resolve the black hole's shadow from approximately 55 million light-years away. The observed shadow diameter of approximately 40 billion kilometers matches predictions for a 6.5 billion solar mass black hole, confirming general relativity's predictions for black hole appearance in strong field regime. The M87 black hole image shows a bright ring surrounding the shadow, produced by emission from hot plasma in the accretion disk, and photons following bent paths around the black hole. The emission is brighter on one side because of relativistic beaming, Doppler boosting of emission from material moving toward observers combined with dimming from material moving away. The asymmetry indicates the accretion disk's rotation direction and constrains the black hole's spin. Subsequent observations produced images of Sagittarius A, the Milky Way's central black hole, showing similar features despite challenges from the source's rapid variability on timescales of minutes. Relativistic jets from accreting black holes produce observable features including superluminal motion, apparent motion faster than light. This illusion occurs because jets oriented nearly toward observers have material moving at near light speed toward us, with light emitted at later times from closer locations, taking less time to reach observers than light from earlier, farther locations. The result is that material appears to cross angular distances on the sky in times shorter than light would require, creating apparent velocities exceeding light speed. Proper calculations accounting for projection effects reveal true velocities approaching but not exceeding light speed, consistent with special relativity. The iron K-alpha fluorescence line from gas near black holes provides diagnostic information about spacetime geometry. X-ray emission from hot coronae above accretion disks irradiates cooler disk material, exciting iron atoms that emit characteristic X-rays at approximately 6.4 kiloelectronvolts in the atom's rest frame. Material in the rapidly rotating inner disk experiences significant Doppler shifts and gravitational redshifts, broadening the line to a characteristic asymmetric shape, extending from approximately 4 to 7 kiloelectronvolts. The detailed shape encodes disk geometry, black hole spin, and viewing angle, allowing constraints on these parameters through spectroscopic observations. Quasi-periodic oscillations, brightness variations at characteristic frequencies, appear in X-ray emission from some accreting black holes, potentially reflecting orbital frequencies near the innermost stable circular orbit. Different models interpret these oscillations variously as epicyclic motions in warped disks, magnetic field oscillations, or relativistic precession of orbits, but all involve strong-field general relativistic effects near black holes. The highest frequency oscillations reach hundreds of hertz for stellar mass black holes, corresponding to orbital periods of milliseconds at a few Schwarzschild radii where relativistic effects dominate. Accretion disks around black holes convert gravitational energy into radiation with extraordinary efficiency. Matter falling toward black holes releases enormous energy through gravitational potential energy conversion, making accreting black holes among the universe's most luminous objects. Understanding accretion disk physics explains how black holes shine despite not emitting light themselves, how they grow by capturing surrounding matter, and how they affect their environments through radiation, winds, and jets. The fundamental reason accretion disks are efficient is the deep gravitational potential well near black holes. For material starting at rest at large distances and falling to the innermost stable circular orbit, approximately 6% of rest mass energy can be converted to radiation for non-rotating black holes, increasing to approximately 42% for maximally rotating black holes. This efficiency far exceeds nuclear fusion, which converts approximately 0.7% of rest mass to energy, making accretion potentially the most efficient energy source in the universe. Accretion disk formation requires angular momentum. Material with no angular momentum falls radially inward on timescales of minutes to hours for stellar mass black holes or days to years for supermassive black holes, releasing energy but producing no lasting disk. In realistic astrophysical contexts, infalling material has angular momentum from orbital motion, turbulence, or magnetic fields, causing it to orbit rather than fall directly. Conservation of angular momentum requires that material cannot fall inward unless angular momentum is transported outward, creating a fundamental challenge for accretion. How does angular momentum transport occur? Viscosity in accretion disks transports angular momentum outward while allowing mass to flow inward, with the process converting gravitational potential energy to heat that is radiated. Molecular viscosity is far too weak to produce observed accretion rates, requiring some enhanced viscosity mechanism. The magnetorotational instability, discovered to operate in ionized disks by Balbus and Hawley in 1991, provides a mechanism for enhanced transport. Weak magnetic fields threading disks become unstable to perturbations that exchange angular momentum between neighboring fluid elements, creating turbulence that transports angular momentum outward far more efficiently than molecular processes. The temperature structure of accretion disks reflects the local energy dissipation rate, which increases toward inner radii where orbital velocities are higher and gravitational forces stronger. Thin disks radiate locally, with each annulus radiating the energy dissipated there, producing temperature increasing inward as approximately the inverse 3/4 power of radius. Peak temperatures reach millions of kelvins for stellar mass black holes and thousands to millions of kelvins for supermassive black holes, determining emission spectrum and observational appearance. Blackbody radiation from different disk radii combines to produce multicolor blackbody spectra, extending from infrared through optical to X-rays, depending on black hole mass and accretion rate. For stellar mass black holes, thermal disk emission peaks in the soft X-ray range of approximately 0.1 to 1 kiloelectronvolt. For supermassive black holes, emission peaks in the ultraviolet or optical. This mass scaling allows distinguishing stellar mass from supermassive black holes through their spectra and provides estimates of black hole masses from spectroscopic observations. Non-thermal emission from hot coronae above disks produces hard X-rays through Compton upscattering, where thermal electrons collide with disk photons, transferring energy to photons and shifting them to higher energies. The coronal temperature and optical depth determine the resulting spectrum, with typical coronal temperatures of approximately 100 million kelvins producing power law spectra extending to hundreds of kiloelectronvolts. The balance between thermal disk emission and non-thermal coronal emission varies among sources and with time, reflecting changes in disk structure and heating mechanisms. Accretion rates vary from far below to potentially above the Eddington limit, the rate at which radiation pressure from emitted light would halt inflow. Sub-Eddington accretion produces thin, radiatively efficient disks where most gravitational energy is radiated. Super-Eddington accretion produces thick, geometrically inflated disks where radiation is trapped in dense material and advected inward rather than escaping, reducing radiative efficiency but allowing rapid black hole growth. Some accreting black holes exhibit apparent super-Eddington luminosities, possibly indicating beamed emission that escapes preferentially in certain directions rather than isotropically. Advection-dominated accretion flows, or ADAFs, occur at low accretion rates where radiative cooling is inefficient compared to dynamical timescales. These flows are geometrically thick, hot, and tenuous, with temperatures reaching billions of kelvins, but densities so low that radiation emission is weak. ADAFs may explain the faint emission from Sagittarius A*, whose luminosity is billions of times below the Eddington limit despite lying at the center of a gas-rich galactic nucleus. The low luminosity suggests most matter captured by the black hole falls in without radiating efficiently, consistent with ADAF models. Jets represent the most dramatic mass outflow from accreting black holes, removing material and angular momentum while also extracting rotational energy from spinning black holes. The Blandford-Zenagic mechanism provides a theoretical framework where magnetic fields threading black hole horizons and rotating with the black holes act as electrical generators, producing electromagnetic power proportional to black hole spin and magnetic field strength squared. This power is carried by Poynting flux, electromagnetic energy flux, which later converts to kinetic energy of accelerated particles, producing observable emission. The launching of jets requires both accretion disks supplying magnetic flux and rotating black holes providing rotational energy. Observations confirm correlations between jet power and black hole spin estimates from X-ray spectroscopy, consistent with rotational energy extraction. However, disk-driven jets powered by magnetic fields in disks rather than black hole rotation may also contribute, and distinguishing these mechanisms observationally remains challenging. The orientation of jets perpendicular to disks reflects magnetic field geometry channeling outflows along the rotation axis where magnetic pressure is strongest. Tidal forces near black holes stretch objects radially while compressing them circumferentially, leading to spaghettification. The curvature of spacetime near black holes produces tidal forces, differences in gravitational acceleration across objects that become extreme near event horizons. Understanding these forces explains the fate of matter falling into black holes and determines whether objects can survive close approaches or are destroyed. Tidal forces arise because gravity decreases with distance, so parts of extended objects closer to black holes experience stronger acceleration than distant parts. For objects falling feet first toward black holes, feet experience stronger acceleration than heads, creating stretching along the radial direction. Simultaneously, gravity pulls matter toward the black hole center, creating compression perpendicular to the radial direction. The combined stretching and compression elongates objects into thin strands, a process termed spaghettification in popularizations. The magnitude of tidal forces scales inversely with black hole mass. For stellar mass black holes with event horizons only kilometers across, tidal forces become extreme at event horizons, tearing apart any normal matter. An astronaut falling into a 5 solar mass black hole would experience tidal forces exceeding body strength at approximately 1,000 kilometers from the event horizon, far outside the horizon, being stretched and compressed to destruction before crossing the horizon. Smaller black holes produce even stronger tidal forces at proportionally greater distances, while larger black holes produce weaker forces. For supermassive black holes, event horizons reach millions to billions of kilometers in radius, and tidal forces at horizons can be surprisingly gentle. An astronaut falling into a billion solar mass black hole would experience tidal forces of only approximately 0.1 Earth gravities at the horizon, entirely survivable, and would cross smoothly into the black hole's interior without noticing the moment of crossing. The tidal forces increase as the astronaut approaches the singularity, eventually becoming lethal, but the horizon crossing itself would be unremarkable from the astronaut's perspective despite representing an irrevocable point of no return. This difference in tidal forces between stellar mass and supermassive black holes reflects the scaling of tidal forces with black hole size. For Schwarzschild black holes, tidal forces at the horizon are proportional to the inverse cube of mass, decreasing rapidly with increasing mass. For Kerr black holes, rotation modifies tidal forces in complex ways depending on location and direction, but the general principle that larger black holes have weaker tidal forces at their horizons remains valid. This gentleness of tidal forces for supermassive black holes means that horizon crossing can be smooth and uneventful, with the dramatic effects occurring only deep inside near the singularity. The time to fall from the horizon to the singularity depends on the black hole's properties and the infalling trajectory. For a non-rotating Schwarzschild black hole, free fall from just inside the horizon to the singularity takes approximately 15 microseconds times the mass in solar masses, approximately 0.7 milliseconds for a stellar mass black hole, or 7 seconds for a supermassive black hole with 10 million solar masses. During this time, tidal forces grow without bound, accelerating structures' disruption until they're torn to fundamental particles and ultimately crushed at the singularity where spacetime curvature becomes infinite. From external perspectives, infalling objects never reach event horizons, instead appearing to slow and fade as they approach. Light emitted from infalling objects becomes increasingly redshifted as gravitational time dilation increases near horizons, with frequencies decreasing exponentially with time. Simultaneously, light intensity decreases because photons become increasingly spread out in time. The combined effects cause infalling objects to appear to freeze at horizons while fading rapidly from visibility, becoming imperceptible within seconds, even to idealized observers with perfect instruments. This difference between internal and external perspectives represents fundamental features of black hole spacetime rather than illusions or measurement artifacts. From infalling perspectives, crossing horizons and reaching singularities occurs in finite proper time, time measured by clocks accompanying the infalling matter. From external perspectives, horizon crossing takes infinite coordinate time, time measured by distant stationary observers. Both descriptions are correct within their respective reference frames, illustrating general relativity's principle that spacetime geometry determines experiences and measurements, with different observers having different but equally valid perspectives. The destruction of infalling matter by tidal forces converts organized structures into particle streams, eventually absorbed into singularities. However, information about infalling matter's initial state may be preserved in the black hole's mass, angular momentum, and charge, the three parameters describing black holes according to the no-hair theorem, or encoded in Hawking radiation correlations as discussed earlier. The question of whether information survives in any form remains central to reconciling general relativity with quantum mechanics. Tidal disruption events occur when stars pass close to supermassive black holes, with tidal forces exceeding stellar self-gravity and tearing stars apart. These events produce characteristic optical and X-ray flares as disrupted stellar material forms accretion disks around black holes, with peak luminosities reaching approximately 10 to the 44 to 10 to the 45 ergs per second, comparable to supernovae. The flare light curves show characteristic decay over months to years as debris settles into accretion disks. Approximately 100 tidal disruption events have been observed, providing information about supermassive black hole masses and spins, and revealing otherwise quiescent black holes at galaxy centers. Time dilation near black holes means time passes more slowly in strong gravitational fields. Gravitational time dilation, the slowing of time in gravitational fields, becomes extreme near black holes, producing effects that dramatically illustrate the relationship between spacetime geometry and the flow of time. Understanding time dilation clarifies why black holes appear black, not because light cannot escape, but because time slows such that external observers never see objects cross event horizons, and explains numerous observational phenomena. The gravitational time dilation factor at a given distance from a Schwarzschild black hole is the square root of 1 minus the Schwarzschild radius divided by the distance. Far from black holes, where this ratio is small, time dilation is negligible. Near event horizons where distances approach Schwarzschild radii, the time dilation factor approaches zero, meaning time slows enormously relative to distant observers. At the event horizon itself, the factor becomes zero, and time from external perspectives effectively stops. This infinite time dilation at horizons means that signals sent from near horizons to distant observers are increasingly delayed and redshifted as emission points approach horizons. Light emitted from matter falling toward black holes experiences gravitational redshift, with frequencies decreasing by the time dilation factor. As matter approaches horizons, emitted light becomes redshifted toward radio wavelengths and below, eventually becoming undetectable. The decreasing signal rate, photons arriving more spread out in time, compounds with redshift to make matter appear to freeze and fade as it approaches horizons. Clocks closer to black holes run slower than clocks farther away, an effect measurable even in Earth's gravitational field, but becoming extreme near black holes. An astronaut orbiting close to a black hole for hours would find that years passed for distant observers, with the ratio depending on the orbital distance. Approaching the innermost stable circular orbit, where orbital periods are milliseconds, hours of proper time could correspond to years or centuries of coordinate time at large distances. The twin paradox, where one twin travels at high speed and ages less than a stay-at-home twin, has a gravitational analog where one twin remains at large distances while another orbits near a black hole. The orbiting twin experiences time more slowly and ages less, returning younger than the distant twin after identical proper times. This thought experiment illustrates that time dilation is not an illusion or artifact of measurement, but represents genuine differences in spacetime geometry that produce real physical effects, including differential aging. Extreme time dilation creates causality questions regarding what occurs at event horizons from different perspectives. External observers see infalling matter asymptotically approach, but never cross horizons, with appearances suggesting that matter accumulates in thin layers just outside horizons, sometimes called frozen stars in early terminology. From infalling perspectives, horizons are crossed smoothly in finite proper time, with nothing special occurring at the crossing point itself. Reconciling these perspectives requires understanding that coordinate systems used by external and infalling observers differ, with different coordinates having different singularities and covering different spacetime regions. Rotating black holes have even richer time dilation structure due to frame dragging, the twisting of spacetime by rotation. Time dilation depends not only on distance, but also on location relative to the rotation axis, and whether observers are co-rotating or counter-rotating with the black hole. The ergosphere, a region outside the event horizon of rotating black holes, is the region where frame dragging is so strong that remaining stationary is impossible. All matter and light must co-rotate with the black hole, though escape remains possible unlike inside the event horizon. The Penrose process exploits the ergosphere to extract rotational energy from black holes. A particle entering the ergosphere can split into two, with one falling into the black hole with negative energy, possible only in the ergosphere, while the other escapes with more energy than the original particle had. The energy extracted comes from the black hole's rotation, reducing its angular momentum. Repeated extractions could theoretically spin down a maximally rotating black hole, though realizing significant energy extraction astrophysically is challenging. Time dilation affects disk dynamics near black holes, with innermost disk regions orbiting faster and experiencing stronger time dilation than outer regions. The Doppler shifts and gravitational redshifts combine with time dilation to produce complex observed spectra from accretion disks, requiring general relativistic modeling to interpret correctly. These relativistic effects produce the broad, skewed iron lines discussed earlier, which provide constraints on black hole spins and disk geometries. Observations of matter in the immediate vicinity of black holes provide tests of time dilation predictions. The Event Horizon Telescope observations of M87 and Sagittarius A probe regions, where time dilation is significant, with photon orbits and shadow sizes affected by time dilation in predictable ways. Future observations with improved resolution may detect time-delayed brightness variations from hot spots orbiting black holes, providing direct measurements of time dilation and additional tests of general relativity. Black holes may serve as portals to other regions of spacetime through wormholes, though this remains highly speculative. The mathematical structure of black hole solutions includes features suggesting connections between distant spacetime regions, wormholes, that have captured imagination despite uncertain physical relevance. Understanding what general relativity predicts about wormholes, what physics might prevent their existence, and what implications they would have clarifies both the scope and limits of current understanding. The Schwarzschild solution, when fully analyzed, describes not just a black hole's exterior and interior, but also a white hole, a time-reversed black hole from which matter and light emerge, but nothing can enter, connected through a wormhole. The Schwarzschild wormhole connects two asymptotically flat regions of spacetime, two universes in the mathematics, through a throat at the Schwarzschild radius. However, this wormhole is non-traversable. Anything entering from one universe reaches the singularity rather than emerging in the other universe, making it useless for travel or communication. The reason for non-traversability is that the wormhole throat pinches off faster than light can cross it. The geometry is such that the wormhole exists for too brief a coordinate time for signals, let alone objects, to pass through before the throat collapses. This feature appears generic for wormholes formed from gravitational collapse. They close before allowing traversal. The Kruskal-Shekker's coordinates that describe the full Schwarzschild geometry clearly show this structure, with the wormhole represented by a region connecting two external universes, but only accessible to particles that arrive at the right spacetime coordinates. Traversable wormholes, hypothetical wormhole configurations, allowing travel between separated spacetime regions, would require exotic matter with negative energy density to hold throats open against gravitational collapse. The averaged null energy condition states that energy density averaged along null geodesics, paths followed by light, must be non-negative for ordinary matter and classical fields. Traversable wormholes violate this condition, requiring matter that violates energy conditions. While quantum fields can produce negative energy densities in special configurations like the Casimir effect, whether sufficient negative energy can be accumulated and maintained to stabilize macroscopic traversable wormholes is unknown. The Morris-Thorne metric describes a simple traversable wormhole, constructed to have no horizons or singularities and to allow objects to pass through with moderate tidal forces. This metric requires exotic matter distribution throughout the wormhole, with the amount and negative energy density depending on wormhole size and geometry. For human traversable wormholes, negative energy requirements might exceed what quantum processes can provide by many orders of magnitude, making such wormholes physically unrealizable even if mathematically consistent. If traversable wormholes exist or can be created, they might enable time travel through arrangements where one wormhole mouth is accelerated relative to the other or placed in different gravitational fields, creating time differences between mouths. Traveling through the wormhole would transport you between times as well as locations. This possibility raises causality paradoxes. What happens if you travel backward and prevent your own trip, leading to the chronology protection conjecture proposed by Stephen Hawking, suggesting that physical laws prevent time machine creation, possibly through quantum effects that destabilize wormholes when closed time-like curves begin forming. The ER equals EPR conjecture proposes that entangled quantum particles are connected by microscopic wormholes, Einstein-Rosen bridges. If correct, quantum entanglement and spacetime geometry would be deeply connected in ways current theories don't capture. This speculative idea aims to resolve black hole information paradoxes by suggesting information isn't truly lost, but rather remains connected to the external universe through quantum wormholes. However, these wormholes would be microscopic, non-traversable, and not usable for communication or travel. No observational evidence supports wormhole existence. Wormholes would produce distinctive signatures, including gravitational lensing, without associated matter, unusual behaviors during potential gravitational wave events, and possibly effects on light or matter passing near their mouths. Searches for such signatures in gravitational wave data and astronomical observations have found no convincing candidates. The absence of evidence doesn't prove absence. Wormholes might be rare, small, or indistinguishable from black holes in current data, but provides no reason to believe they exist. The theoretical possibility of wormholes illustrates general relativity's richness and the existence of solutions with surprising properties. However, the gap between mathematical possibility and physical reality is enormous. Many solutions to Einstein's equations describe spacetimes that probably don't exist in nature because they require special initial conditions, violate energy conditions, or are unstable to perturbations. Wormholes likely fall in this category, interesting mathematical structures that illuminate theory's properties, but that don't correspond to real astrophysical objects. Black holes play crucial roles in galaxy evolution and cosmic structure formation. The influence of black holes extends far beyond their immediate vicinities, with supermassive black holes at galaxy centers affecting their hosts' evolution and possibly contributing to cosmic structure formation. Understanding these broader impacts reveals black holes as important astrophysical actors rather than merely exotic curiosities. The correlation between supermassive black hole masses and galactic bulge properties suggests tight evolutionary coupling. The M-sigma relation shows that black hole mass increases with bulge velocity dispersion, the random velocities of stars in bulges, across 4 orders of magnitude in mass, with approximately 20 to 30% scatter. This correlation is surprising given that black holes comprise only approximately 0.1% of bulge masses, suggesting that despite their small fractional mass, black holes somehow influence or trace bulge assembly. AGN feedback, the energy and momentum injected into galaxies by accreting black holes, provides the most widely accepted explanation for black hole-galaxy correlations. Jets, winds, and radiation from AGN heat surrounding gas, sometimes expelling it from galaxies entirely. This heating prevents gas cooling and forming stars, potentially regulating both star formation and black hole growth. When black holes reach masses such that feedback balances gas accretion, both black hole and bulge growth halt, creating correlations between final black hole mass and bulge properties. Observational evidence for AGN feedback comes from multiple sources. X-ray observations reveal cavities in hot gas around radio galaxies where jets have displaced gas. Optical spectra show high-velocity outflows with speeds reaching thousands of kilometers per second, and mass loss rates exceeding star formation rates in some galaxies. Simulations of galaxy formation cannot reproduce observed galaxy properties without including AGN feedback, requiring energy injection from black holes to prevent excessive star formation in massive galaxies. Quasar mode feedback occurs during intense accretion phases when black holes shine as luminous quasars, with radiation pressure and winds driving gas from galaxies. This mode is particularly important at high redshifts corresponding to cosmic epochs of peak quasar activity and star formation, possibly explaining why quasar activity and star formation both peaked approximately 10 billion years ago. Radio mode feedback operates during lower accretion phases when jets rather than radiation dominate energy output, with jets inflating bubbles in hot galactic halos that suppress cooling flows and star formation. This mode is important in massive elliptical galaxies and galaxy clusters, where AGN prevent runaway cooling. The co-evolution of black holes and galaxies through cosmic history is traced by comparing black hole demographics at different redshifts. The most massive black holes and most luminous quasars appear early, less than 1 billion years after the Big Bang, suggesting that early conditions favored rapid black hole growth. The quasar space density peaked at redshifts around 2 to 3, approximately 3 billion years after the Big Bang, when cosmic star formation also peaked, consistent with parallel evolution. At later times, both star formation and black hole growth declined, with most supermassive black holes today being quiescent with low accretion rates. Galaxy mergers provide mechanisms for funneling gas toward black holes while also merging the black holes themselves. When galaxies collide, gravitational torques drive gas inward, potentially triggering starbursts and AGN activity. The supermassive black holes in merging galaxies form binary systems that eventually merge, emitting gravitational waves at frequencies detectable by future space-based detectors like LISA. Merger simulations suggest that multiple generations of mergers build the most massive galaxies and their central black holes, with merger trees tracing formation hierarchies from first seed black holes to present supermassive ones. The distribution of black holes tracks dark matter distribution since both respond to the same gravitational potential wells. The most massive dark matter halos host the most massive galaxies and black holes, creating correlations across cosmic structure. Black hole mergers trace cosmic structure assembly, with merger rates providing constraints on structure formation models and cosmological parameters. Gravitational wave observations of supermassive black hole mergers, expected from LISA, will probe structure formation across cosmic history. Black holes contribute negligibly to cosmic mass budget. Even summing all black holes gives only approximately 10 to the negative 5 times total matter density, so they don't affect large-scale structure formation gravitationally. However, their energy output during AGN phases heat's intergalactic medium and may affect structure formation indirectly by preventing gas accretion onto galaxies and galaxy clusters. This heating contributes to the entropy floor observed in intergalactic medium, requiring energy injection beyond gravitational heating, with AGN feedback as a leading candidate. The final parsec problem describes challenges in bringing supermassive black hole binaries from kiloparsec separations after galaxy mergers to final merger. Dynamical friction shrinks binaries until reaching approximately 1 parsec separation, but further shrinkage requires mechanisms like three-body scattering with stars or torques from circumbinary disks. Whether binaries stall at parsec scales or merge within cosmic timescales depends on uncertain dynamical processes, affecting predictions for gravitational wave event rates from supermassive black holes. If you're still awake somewhere in this exploration of black holes, of event horizons and singularities, of gravitational waves and accretion disks, of time dilation and the warping of spacetime itself, there's more to discover, more quiet facts about the universe's most extreme objects. But if sleep has found you, if consciousness has faded somewhere between the stars, then rest knowing that black holes continue their patient work, shaping galaxies, swallowing matter, warping spacetime in ways we're only beginning to understand. While you sleep tonight, black holes throughout the universe continue their existence, attracting matter through immense gravitational fields, spinning in the darkness at rates that drag spacetime along with them, slowly evaporating through Hawking radiation so weak that for stellar mass and larger black holes, it will take inconceivably long times, far longer than the universe has existed, to have any noticeable effect. The supermassive black hole at our galaxy's center, Sagittarius A, continues its slow consumption of gas and occasional stars, producing faint radiation from the tortured matter in its accretion disk, rotating once every few tens of minutes despite containing 4 million solar masses. The black holes formed in supernovae continue marking the deaths of massive stars, the stellar cores collapsing in seconds to objects so dense that their Schwarzschild radii encompass what was once the center of a functioning star. The gravitational waves from merging black holes continue washing over Earth, perhaps several every day from across the cosmos, too weak to notice without LIGO's extraordinary sensitivity, but carrying information about cataclysmic events where black holes spiraled together and merged, releasing energy that briefly outshone all the stars in the universe combined. The mathematics that predicted black holes before any were observed continues to reveal new features, new possibilities, new connections between gravity and other physics. Theorists continue wrestling with the information paradox, seeking to understand whether and how information can escape from black holes, whether firewalls exist at event horizons, whether black holes connect to distant regions of spacetime through quantum entanglement. These questions connect the very large, astrophysical black holes to the very small quantum mechanics, in ways that may eventually lead to theories unifying all forces and resolving the contradictions between general relativity and quantum mechanics. The Event Horizon Telescope continues its observations, aiming to produce movies of matter orbiting near black hole event horizons, to measure black hole spins from the shapes of their shadows, to test general relativity in the strongest gravitational fields accessible to observation. LIGO and Virgo continue detecting gravitational waves, characterizing populations of black holes across the universe, measuring their masses and spins, testing whether they match predictions from stellar evolution, or whether exotic formation channels produce some black holes. LISA, planned for launch in the 2030s, will extend gravitational wave observations to lower frequencies where supermassive black hole mergers radiate, opening entirely new windows on cosmic structure formation. The question of what lies at singularities remains unanswered and may remain forever unanswered since singularities are hidden behind event horizons, preventing direct observation. Quantum gravity, whatever form it ultimately takes, may resolve singularities into something less pathological, perhaps regions of extreme but finite curvature governed by quantum effects, perhaps connections to other regions of spacetime, perhaps something we cannot currently imagine. The cosmic censorship hypothesis suggests we'll never need to worry about naked singularities affecting the external universe, though this conjecture remains unproven and counterexamples exist mathematically, even if not physically. The role of black holes in cosmic evolution becomes clearer as observations and simulations improve, revealing how AGN feedback shapes galaxies, how black holes grow in tandem with their hosts, how mergers build both galactic bulges and central black holes through cosmic history. The co-evolution of black holes and galaxies represents one of the major discoveries of modern astrophysics, transforming understanding from a time when black holes were considered exotic curiosities to recognition that they're central actors in galaxy evolution, with most large galaxies hosting supermassive black holes that have profoundly affected their development. The next time you look at the night sky, consider that you're seeing photons that traveled across space for years or centuries or millions of years. Photons that may have passed near black holes on their journeys, having their paths bent by gravity, their wavelengths shifted by gravitational redshift, their polarization rotated by frame dragging. Consider that the darkness between stars contains black holes, stellar remnants scattered through the galaxy, intermediate mass black holes perhaps lurking in star clusters, the supermassive giant at our galaxy's center presently quiet, but having been violently active in the past. Consider, too, the implications of black holes for our understanding of reality. These objects demonstrate that space and time are not fixed backdrops against which events occur, but are themselves dynamical entities that can be warped, curved, stretched, and possibly even torn. They show that the universe permits extremes far beyond our everyday experience, objects where gravity overwhelms all other forces, where matter is compressed to infinite density, where time itself slows and stops. They reveal that the mathematics of general relativity, despite being a century old, continues making predictions about nature that observations confirm even in regimes Einstein himself doubted could exist. Black holes stand as monuments to the power of theoretical physics, to the ability of mathematics to describe reality, and to the universe's capacity to surprise us with phenomena that seem impossible yet undeniably exist. They challenge our understanding while inviting us to understand more deeply, to reconcile quantum mechanics with gravity, to explain how information behaves at event horizons, to determine whether wormholes exist, to discover what lies at singularities. These challenges will occupy physicists for decades or centuries more, continuing the tradition of using black holes as laboratories for testing the most fundamental ideas about space, time, matter, and gravity. See you next time.